polynomial functions in their graphs. Hopefully it sounds works. This section is pivotal, and maybe I've said that for every section so far. So, but this section, in terms of graphing, we've had initially a section in chapter 1 dealing with graphing a straight line, so straight line equations. And then after that, the next phase of graphing was to consider those 6 basic graphs, and then just do the shifts, vertical shifts up, down, left, or right, maybe a mirror image, symmetry. You can flip the graph. If you know the image of one, you can just look at the mirror image and get the other translation. We talked about those. And then after that, the third phase was to deal with just a parabola. And that was the last thing that we did. And so we focused on finding the vertex of the parabola, and then for the vertex, x-intercept, y-intercept, be able to plot that parabola. Now here, this phase of graphing is for any polynomial of nth degree you want to be able to graph. And we can do that based on the steps here. Now, in leading up to all these equations focusing on graphing, once we get through with this section, there's still going to be basically one more function to graph. Jordan River must be crossed, we got one more river to cross. So later on we'll talk about trying to graph a rational function. That is something that looks like 1 over x. It has holes there because if you have a fraction function, that denominator has trouble when the values are 0. So you know you can't have 1 divided by 0, that kind of thing. So anytime for those rational functions you have a 0 downstairs, something strange happens. We can't talk about those now. I mean, who cares? Because we haven't even gotten to polynomial functions in their graphs. So, but just to kind of give you the larger scheme of things, so you know from whence we've come and where we're going. Now, why is that important? It should be important just with the philosophy of life. You shouldn't plan your day, you shouldn't operate within the day if you don't know your purpose for that particular day. And so, and then likewise, your purpose for life itself. You know the purpose thereof, then you can operate within the particulars. So, so where we're going, might not be able to get there, but at least we got an idea of where we're trying to get to. So, with that in mind, this section that focuses on graphing these so-called polynomial functions has some steps, and we'll talk about those steps. And what I did was to put a page or two in here with my own notes to try to help you out. It's kind of funny. 20 years ago, when I was teaching this class here, some of the concepts that they now cover in this class, in this section, we didn't cover 20 years ago. And so then my son, who came into Calhoun, took this class 2 years ago. Some of his friends were asking me about some of the concepts in this particular section. And my response was, you don't need all that. There's an easier way. So I'll show you, what they present here in this section, and then I give you what I think is hopefully my way, and you just choose whichever way you think is better. So let's see. So here are the objectives for this section. all, we want to define a polynomial function. And so we said that a function has nth degree, and here n is non-negative. That means that this function, the power is not negative. That means that the values don't drop down to the denominator. And n is important, so we call that n the degree of the function. And a sub n is just the coefficient that we call the leading coefficient. So two things that we want to definitely pull out from this definition of the function, just two things, and that is this number n and then this a sub n. So n here, we call that the degree, and then the a sub n, we call that the leading coefficient. It'll be important because we'll talk about the leading coefficient test. So now a sub n, don't be scared about that. It's just the number that's associated with x to the n. Like if you take this example here, our a sub n, the leading coefficient, would be the -3. So a sub n is the -3. It's just the number that's associated with x raised to its highest power. So the degree is just the highest power, right? So for this one, see that n is 5. Let's look at g. Now g, the function is broken up. That is, it's already factored. So to be able to get the degree, that is the highest power, I mean, you can multiply that out, which is what they do, but you don't have to. You can just count up the power. This is x to the 4th, right? And this is the first power. First power says 4 plus 1 plus 1, we get x to the 6th. Right? So 6 is the degree. And then the leading coefficient would be, now if there was a number inside where it says x minus 2, if there was like, let's say for example, 4x, I would multiply the -3 times the 4 times the 1 to get the leading coefficient, a sub n. But here it's just -3 times 1 times 1, which is just -3. The leading coefficient, a sub n, for that one would be -3. Now on the right side, it talks about these functions that are not polynomials, and they say that because of how the polynomial is defined on n. N is said to be non-negative, and it's said to be also an integer. So these integers, the set of integers, or these whole numbers in also their so-called negatives. Set of integers. So if you look at this guy, its power is the 1/2. Well, that's not an integer. It's a fraction. Notice that the integers don't include the fractions. Right? So here, this would be not a polynomial. Now look at capital G downstairs. Why is that not a polynomial? Because here this degree is -2. We said that here we're looking at polynomial functions of nth degree where n is non-negative. So this is things that we can kind of X out in terms of what we're talking about and what we're not talking about. Our focus here for these polynomials, when they exclude these negative powers of the exponents, what they're doing is they're trying to force the graph to be smooth, continuous curve. So here, smoothness simply means that the curve has no breaks, no sharp turns, like a sawtooth, like it goes in it takes a dive. Look at over here on the right, you see these sharp turns and corners. Well, there, those graphs are not smooth, and we call them that they are discontinuous. Here, this particular graph has a jump. It has a hole there, right? So what we're going to be focusing on are the so-called smooth functions. Now, in calculus, we define more refined in terms of exactly what that means. So we have strict definitions according to mathematics to define continuity, and then we deal with this idea of differentiability as well. But right now, I tell you what, folks, this is the key. This section right here, man, this is it right here. I mean, I want you to mark that. If you got your book or your notes, whatever, you just mark somewhere that if you can get this section, this is like one of the big crutches for calculus. This stuff. You can get this. There's going to be a section in calculus called extrema, relative minimums, relative maximums, applying the first derivative test. You have to make use of this stuff right here. So if you get this now, man, it's going to save you a whole lot of trouble later on. And it's so crazy because, I mean, this information just comes out of algebra. I mean, that's the whole glory behind it. I mean, think about calculus being difficult. Man, calculus is just algebra. Calculus is the algebra, and it's also the trigonometry. So just two things work, and if we get those two, then calculus is easy. Easy peasy. So, talk about the end behavior of a polynomial function. Two things we want to look at. That is, one, we want to be able to know what is n, what's the degree of the polynomial, and then also what is the leading coefficient. We call this the leading coefficient test. So what we're going to be able to determine are the so-called end behaviors of the graph. The graph is going to either on the end is going to go up to the left, go up to the right, or they're going to drop on the left and the right, or they're going to do something like this, John Travolta, or they're going to do something like that. Right? You know, staying alive. Anyway, so when do they do this? You know, put your hands up. Or when do they do the graph does this? It's just the end behavior. Now, there's going to be some stuff that goes on in between. We got to figure that out. But for right now, for this leading coefficient test, just what happens both up, both down, or John Travolta. So, here's what we have. First, we consider if n is odd, if that number n is an odd number, if the leading coefficient is positive, then the graph would fall to the left and it's going to rise to the right. And I'll give you an example of that. Again, if the degree is odd, and if the leading coefficient is a negative number, then it's going to rise to the left, it's going to fall to the right. Then, the third possibility, if n is even, leading coefficient is positive, then on the far left or right, it rises. If n is even, leading coefficient is negative, then it falls both to the left and to the right. Now, here are the examples for all four, and then it all makes sense. So, example 1, here f of x is equal to x to the third. I'm going to give those basic graphs. So notice here that n is 3 is odd. A sub n is the number multiplied to this variable. It's just 1, so it's positive. So that means that it's going to fall to the left and rise to the right. But just think about the graph. Think about the graph. Falls to the left, it rises to the right. Now take the same function, put a negative in front of it, and so then the graph just flips. Let's call it g of x is equal to negative x to the third. So here is 3, it's odd. A sub n is negative 1, is negative. So it's going to rise to the left, fall to the right. So this graph just does the opposite here. Again, all I have in my mind will be these 4 simple graphs. That's all I got. Because if it's an image, if it's a picture, there's 2 things that people don't forget. We don't forget pictures and we don't forget stories. I preach a sermon and I got like 8 points, folks forget all that. I get up there and talk about a story, they remember the story. If you see something that happened, you see an accident, you remember that. Other stuff, we don't remember. Example 3, h of x is equal to x squared. Here n is equal to 2. A sub n is equal to 1. It's positive. So you just look at the graph first, and then you know how the MTH work. That rises to the left and rises to the right. And then the 4th example. Or negative x. Here's 2. This way, it falls to the left, it falls to the right. Just the end behaviors that we did. Now in between, we got to figure that out. How many times I can do that, right? My wife and I were arguing on this dance, you know, you get on the floor, and we call it in Indianapolis, we call it the California word. Have you heard that phrase before? Or have you heard of the snake? You know, you get on the floor, and she's from New York, so they call it the snake. And so in Indianapolis, we call it the California one. She looked at me and she was like, y'all are very weird. Okay, so let's look here at this example. What is n? We're trying to determine the n behaviors. What is n? What's the degree here? N is equal to what? Did you say 6? Do you see that? You got times the powers, right? So if you multiply this out, it's going to be x to the third, this is x to the second, this is x to the first. That's 3, 4, 5, 6, right? X to the 6. So it's even. The leading coefficient, a to n, is at -4. Negative. I apologize that this graph over here does not match this function right there. That is good. I do apologize for that. I guess I meant this to be separate examples. So let's look over the left. I apologize for backtracking. I'm looking down here. So here for this example, different from the one on the right, n is equal to 3, and a to n is 1. So this guy is odd, and this is positive. So it falls to the left and rises to the right. And you can see that. Now, for this example, all we're determining is just the n behavior. So since the degree of 6 is even, and since a to n is negative, this is going to fall to the left and also fall to the right. All right, what about this first checkpoint 1? N is 4, that's even. A to n is equal to 1, positive. So it acts like x to the second, so this is going to rise to the left and also rise to the right. What about down here? What is, notice this. So what is n for this one? What's the degree? Isn't it 5? 3 plus 1 plus 1, right? This is the first degree. You know, when you're multiplying x to the third times x times x, you get x to the 6th. Here, n is equal to 5. The leading coefficient is 2. It's positive. So this guy acts like, for the n behaviors, it acts like x to the third. So it falls to the left, then it rises to the right. We'd like to talk about the zeros of the polynomial function. So if that's a new term for you, let me tell you, what you've been doing all your life in terms of factoring an equation, well, that term factor, when you get those linear factors, each factor is a zero. So the zero of a function is just what we say the solution of a function. That means that that's an x-intercept. They all mean the same thing. So when you hear the term zero of a function, we're not talking about, the zero. It could be x equal to 5. But at x equal to 5, what they're saying is that y is equal to 0. It's the x-intercept. So on the test, if I say, what are the zeros for the function? You better not write a 0 down there. I've had that happen. Get out of here, right? What is 0? I know what a 0 is, but anyway. Okay, so the zeros of the function is the same terminology for the root. And if you're from the South Alabama, it's root, right? Which is what I say. Or it's the factor. factor something, I get those linear factors. If I get x minus 4, it means that x equal to 4 is the x-intercept or the 0. So, multiplicity of zeros. You know, this was something that I remember, again, some EJ's high school friends, they were asking me some questions about this. This is one, like the zeros. Yeah, it's very easy. It's nothing hard about the so-called multiplicity of zeros. All that simply means is if you can factor, hopefully you will be able to factor that function, then you look at the power of the factors. And that power tells you the so-called multiplicity. That simply means how many times does this factor occur? So look down here at this example. You see this has been factored. You get x plus 1, very quick. See, you also get 2x minus 3 to the second. So this means that, look, I got x equal to negative 1. If x plus 1 is a factor, if x plus 1 is a factor, then x equal to negative 1 is a 0. So I get x equal to negative 1, and then I also get, look at this one, you set 2x minus 3 equal to 0, and that implies that x is equal to, you see that, 3/2. Now x equal to negative 1 occurs once because its power is 1. And x equal to 3/2 occurs twice because its power is 2. So that power represents the multiplicity. How many times does this root occur? Right. So here, so x equal to negative 1 has multiplicity of 1, and x equal to 3/2 is multiplicity of 2. Here we're looking at the power. Does that make sense? So then they talk about even multiplicity or odd multiplicity. That is that if the root occurs 1 time or 3 times, then we say it has an odd multiplicity. If it occurs 2 or second power or fourth power, then we talk about here so-called even multiplicity. Now look at the statement. If R is a x-intercept, has even multiplicity, then the graph touches the x-axis and turns around at R. Now that's some good jargon, but I'm going to try to draw it out so you can see it. And I'm going to show you just based on something that we know. If R has a 0, that is the x-intercept of odd multiplicity, that is the power of 1, 3, or 5, then the graph crosses the x-axis at R. Doesn't make any turns, just keeps on going, it just does a little wiggling. All right? And here's what they're saying. I want you to think about this. Again, we always resort back to some of those basic graphs. So here's what I do. So here, let's take f of x equal to x squared. That is that x equal to 0 has multiplicity of 2. Now watch what this graph does at 0. You know it's a parabola, right? It's a parabola. And we know that at 0, check that, look at that graph. That parabola does not cross the x-axis, it just touches. See that? That's all we're talking about. That's all we're talking about. That mug, look, that one of those deacons in the church, he still used the old phrase, you know, mug. You know, that little MTH talk, you know, man. What that mug talking about? Look, that mug turned around right there at x equals 0. I heard the old dude, I said, man, you too old to be saying that phrase. Oh, boy. So anyway, see, that's what they're saying. Here, if it has an even multiplicity, it touches, and then it turns around. Okay. You don't want me to say? No, nobody does. Okay. So then, look at this one. G of x equals to x to the third. Here, x equals 0 has multiplicity of 3. All right. Let's say we never saw this statement here before, but I know this graph. And I know at 0, look, it doesn't really turn it around. It just keeps on traveling, but it does some kind of wiggling, you know, up in there. But it's still moving in that same direction. And it's like that snake shape. So here, that's what they're saying. If R is a 0 of odd multiplicity, then the graph crosses. Well, that's what this graph did for x to the third. It crossed at that x-intercept. Right? Does not turn around. So that's what they're saying. So in my head, always I have that the graph for x squared or the graph for x to the third. It kind of keeps me balanced. Yeah. All right. All right. So here, finding the zeros and their multiplicities. So what are the zeros? Yeah. I'll repeat myself. Let's look at check 27. Oh boy. All right. So what are the zeros down here for check 27? That's equal to, what's the first one? You know, again, to find the zeros, it's the x-intercept. We set the function equal to 0. We solve for y. So what that ends up being is just x plus 1 equals to 0. And 2x minus 3 equals to 0. Then you get x equals to -1 and x equals to 3. So down here, wouldn't that be x plus 1/2 equal to 0? So x is equal to -1/2. And it has multiplicity of what? Of 2, because of its power, right? Multiplicity of 2. And then we have, what's the next 0? The x-intercept? X equal to what? 5. And it has multiplicity of what? 3. Now, if it has an even multiplicity, that means that it's going to touch the x-axis. here, this guy just touches. And that's equal to negative 1. If it has odd multiplicity, then the graph is going to cross at x equals 5. The intermediate value theorem for polynomials is based off of what we just got to talking about in terms of these, if the graph touches at the x-axis or if it crosses, and particularly if it crosses the x-axis. How are we able to determine sometimes if it crosses? Well, we can if we know that on a particular interval, the function changes sign. If it goes from negative to positive, it has to mean that it's crossing the x-axis. If it goes from positive to negative, that means that it's crossing the x-axis. We don't see that if it has multiplicity that's even, because it's going back the other way. So what the intermediate value theorem simply says that if f of A and f of B have opposite signs, that is that if one is negative and the other is positive, or if one is positive, the other is negative, then there is at least one value that we call C between A and B such that f of C is equal to 0. All they're saying is this. That some function f is A, this is B. So here for A, then for B. Now notice that f of A is less than 0. It's downstairs. It's negative. The y value is negative. F of B is above the x-axis. It's positive. That means that in between A and B, that graph has to touch down and cross the x-axis. That's all they're saying. So here we guarantee the 0. The intermediate value theorem. This implies that there exists a C such that f of C is equal to 0. That's just what that theorem says. There exists this. We call this an existence theorem. Something exists. It doesn't tell us how to get C, but it tells us that C is there. Well, this is fascinating. So all you're going to be able to do is take a function, check between two values to see if the sign changes. Look, at f of 2, we get negative 1. At f of 3, we get positive 16. So if we went from negative to positive, that means that we have to cross the x-axis. That's all it's saying. Does that make sense? Does that make sense? That's all they're saying. Let's go to intermediate value. Pretty cool stuff. We're at Rolle's theorem and the mean value theorem in calculus 1 to this. As a matter of fact, we'll come back and introduce the same theory there in calculus. So you got it here. Can't say you didn't see it. So can't get to the pearly gates and say nobody told you about it. Well, we might not ask you about the intermediate value. Anyway, let's move on. We got to work some problems. Turning points of polynomial functions. So now I want to get in between. We talked about the leading coefficient test that told us what happened on the end. You know, if it rises to the left and right, falls to the left and right, or if it does John Travolta. But now what happens in between? We can determine what happens in between based on the multiplicity. You know, if it's the even multiplicity, then that means that it's going to turn. If there's an odd multiplicity at that particular zero, it's going to cross the x-axis. So here, notice, and notice this, that if n is the degree that the graph of F has at most. At most is kind of misleading. It has at most n minus 1 turning points. If it has at most 5, that means that it could be none, 1, 2, 3, 4, 5. At most 5 doesn't mean it's guaranteed to be 5. At most 5 means that it could be 0, it could be 1, 2, 3, 4, 5, that kind of thing. So to graph these polynomials, this is what they give in the book. I think that's pretty good. We're going to go through these steps. So, first apply the leading coefficient test, and then after that, determine the multiplicity. That's step number 2. And then if we have even multiplicity, then we can talk about that the graph it touches at the x-intercept. If k is odd, then the graph will cross at that particular intercept. We can find the y-intercept by just setting x equal to 0, and then check symmetry. And then we can look at the turning point. Now here's what I've submitted. So these are just from my notes. Apply the leading coefficient test. Factor and find all x-intercepts, the zeros. Find the y-intercept also. Divide the number line based on the x-intercept. Man, this is how I used to do it, man, back in the day. Every time it worked out. Divide the number line based on the x-intercept. Determine the sign, if it's plus or minus on the sub-interval. If the sub-interval is positive, that means that the graph is going to be above the x-axis. If I get a negative for that interval, I just test a point on the interval. If I get negative, the graph is going to be under the x-axis. That's all I mean there. That will automatically tell you those dang on turns and crosses. See, to me, this idea of turns and crosses is very new. I mean, the author just put that in recently, a few years ago, after I went on to figure out the thing. So I was like, what's wrong with our old method? Can't be anything wrong with it. But anyway, number 4, I think with the information that we have, we should be able to put it all together. Again, this is only approximation. We're not guaranteeing the actual graph, because we cannot determine the actual, if there's an actual maximum or the actual minimum where they are without calculus. In calculus, we talk about the first derivative test, second derivative test, and then you'll be able to easily figure out those. So here we're just sketching this just on the approximation. Well, let's see. Here's the graph on the right. Is it a polynomial? Is this a polynomial? We were talking about that in the very first slide. It's not, because look, it has some jumps, right? It has some holes there. It's not smooth. Remember we said the polynomial has to be smooth. Right? So we're looking for something that Isaac Newton said was smooth. No. Votes no. All right. Use the leading coefficient test to determine the end behavior of the graph. And we got 1, 2, 3, 4 equations. Want to match up the graph by based on the end behavior. Right, so look at 15. So 15 here n is 4. That's even. A sub n is -1. That's negative. So that means that for that particular graph, the end behavior is going to be falling to the left and falling to the right, right? So let's see if we can find a graph of the 4 that does that. Looks like this one. So I'll just say number 15. Is that what you said too? Falls to the left and falls to the right. Look at 16. Well, that's going to fall to the left and rise to the right. Say that one. I'm not doing all that. Right. So what about 17? You tell me. Which one is that? Which graph is 17? See, it's the last one, right? Because here n is 2, is even, a sub n is 1. Positive. And just by default, this has to be 18. So, you know, that 18 does the opposite of 16. So it's going to rise to the right and fall to the left. Very good. All right. What do you say about this one? Use the linear coefficient test, and what can we say about the end behavior? Which one was that there? A, B, C, D, E. Does everybody agree? That is A. Huh? What's the degree? The degree is 7. What's the leading coefficient? Leading coefficient is 8, right? So 8 is positive, and the degree is odd, so it's going to fall to the left or out to the right. What about this one? All right, work that one out. I'll be back.
own stuff. How you gonna come up with your own stuff? But the math guy gets you deeper. He a preacher. And you know what preachers do. And if you get it, you get it. If you don't, you don't. That's how you get like in the church, like you can sit up there and talk about God all day. But if you decide that, oh, okay, I'm gonna accept what he said, and I'm gonna take it home, and I'm gonna go like this. You know, if you be alright, but if you see a church and you be like, okay, it is what it is.
All right.
And you got it too.
You got it? Okay, so find the zeros for this polynomial function, and then give the multiplicity of each zero, and then take whether the graph crosses the x-axis or touches the graph and turns around at each zero. So first of all, we find the zero, and you see that x is equal to 1 and x is equal to 4, right? We all got that? Okay, good. It says now determine the multiplicities of the zero. So here the power of x minus 1 is 1, so it has x equal to 1 has multiplicity of 1, and then x equal to 4 has multiplicity of 2. So let's see. So there are 2. So we know it's not going to be b or c because we have 2 zeros. So the multiplicity of the smallest zero is 1, and the multiplicity of the largest zero is 2. Right? Okay. Same function, just more questions. Determine the behavior of the function at each zero. Select the correct choice below. If necessary, fill in the answer boxes with your choice. So here, the graph crosses the x-axis, that blank touches the x-axis and turns around that blank. For B, the graph touches the x-axis and turns around at all zeros. C, the graph crosses the x-axis at all zeros. Let's write what we know. We know that at x equals to 1, it has odd multiplicity. And that implies that there's odd multiplicity. Remember, that's acting like x to the third, so that means it crosses. So this implies that if crosses the x-axis at x equals to 1. Now, at x equals to 4, it has an even multiplicity. So that puts us in the mind of x to the second. So for that, it just touches. So here, it touches the x-axis at x equals 4. So let's see. So here, so we know it's not going to be B or C because it's doing two different things. At x equals 1, it's crossing, and x equals to 4, it's touching. So the graph crosses the x-axis at x equals to 1. It touches the x-axis and turns around at x equals to 4. You give me some? Okay. Weird noise. I'm not hungry. No, I don't know what's going on. I had Cheerios this morning. Yeah, Cheerios. Maybe it was too early. I had one of the pastors in Indianapolis asked me yesterday or the day before yesterday if I would come on to their prayer line and do dedication, intercessory prayer. I said, yeah, no problem. And didn't know it was going to be at 4 o'clock this morning, so It was funny. It was good. Oh boy. So, so the same problem here, but just apply to this problem. So same question, different function, right? So find the zeros. So to do that, we got to factor. So you notice that there's an x that's common in all three. Just factor out an x, okay? We have x times then x squared minus 34x plus 289. Then I need to come up, if I can factor this, what's in the parentheses, if we can find two numbers that we multiply, we get 289, but when we add them, we get negative 34. And I was like, why such a big number? I mean, whatever happened to 25 and 16? Numbers that we like. Even 64, we'll take that. 81, we'll take that. 99, right? 99. Okay, anyway, so what about 17 times 17, right? Isn't 17 times 17 289? Well, there you go. So this is x minus 17 times x minus 17. So here our zeros would be 0 and 17. We'll have to say 17 twice because that's what the multiplicity of 2 would represent. Right? So we only have two zeros. So if you think about it, you write that out, you can see this is x times x minus 17 to the second power. So that x equals 0. That'll be the first factor, right? We have multiplicity. What's the multiplicity here for this x? That would be what? Multiplicity of what? Multiplicity of 1 is x to the first power, right? So since it's odd, then it crosses. And then at x equals to 17, we have multiplicity of 2. Look, I'm looking at the power. Right? For that multiplicity, I'm looking at the power. We have multiplicity of 2. That means that it touches. The x-axis. So again, there are two. Multiplicity of the smallest zero, that's at x equals 0, that guy is 1. And the multiplicity of the largest zero is 2. So, now, don't throw away factoring because we got to use the factor. Determine the behavior of function at each 0. So we got two things happening because at x to the first, at that guy, it's going to, his eye is going to cross. So the graph crosses the x-axis at x equals 0. And we get x equals 0, then x equals 17. And the graph touches the x-axis and turns around. And I guarantee you, you'll be singing that song after a while. Use the intermediate value theorem to show that the polynomial has a real zero between the given intervals. Who can tell me what does the intermediate value theorem say? In your own words, as I know. What does that, what does the intermediate value theorem say? You remember? Oh, this is a lively bunch. Oh, we're so excited. Eleanor. I think I read your facial expression. The intermediate value theorem says what? It says that if I can evaluate the function at 2 points, and if I get change in sign, one is negative, the other is positive, or one is positive, the other is negative, then that means that the graph crosses the x-axis, so there has to be a zero somewhere in between. So they want you to find first f of 1. So this is 1 to the third minus 1 minus 4. So this is 1 minus 1 minus 4 is negative 4. That's positive. Now find f of 7. So this is 7 to the third minus 7 minus 4. So what is that? That's 332. It's positive, right? It's negative. So it says f of 1 is negative, so I'm looking for that. So f of 1 has to be less than, so I get b is less than. But then it says f of 7 is less than, no, f of 7 is positive. So I have to go down to d. F of 1 is equal to negative 4. F of 7 is equal to 3. 32 is positive. See how the signs change? Go from negative to positive? It means that we crossed the Alabama line. Right? We made it into Tennessee. Right? We're almost there on the underground. Right. So, answer these parts. So first part, given this function, can we determine the leading coefficient based on leading coefficient test? So what will we say here about the leading coefficient test? It tells us what about the end behaviors? You see there that n is 3, it's odd. And ace of n, the number that's multiplied to it, right, is 1. It's positive. So it's acting for its end behaviors, it's acting like x to the third. So it falls to the left and rises to the right. So the graph falls to the left, rises to the right. Is that C? Is that right? Is that C? Find the x-intercepts. Again, the x-intercept is the same thing as the factors or something. Zeros. Well, I try to factor this. Looks like all the problems they gave us, for the preliminary part, everything was already factored. So here I got a factor. So look at the first two pairs, and there's something common. Looks like an x squared. With x plus 4. Look at the second two pairs there, is a negative 1 that's common. Parentheses x plus 4. And then it looks like I can factor out the x plus 4. Right? So this is x plus 4 times what I have left is x squared minus 1. So that can be factored further. So I get x plus 4 times x plus 1 times x minus 1. examples, they were giving you stuff that was already worked out. That wasn't nice. That's no work for you. I mean, when it's already like it is, naturally, you can see that here, n is 3, and the leading coefficient, a sub n is equal to 1. So it's going to fall to the left and rise to the right. Now you set this guy equal to 0, and then we can clearly see that x equals to -4, x equals to -1, x equals to 1. These are our x-intercepts. Same thing as the zeros. Look at the linear factor, x plus 4, that implies x equals to -4 is a 0. X plus 1 is a linear factor, x equal to -1 is a 0. So here are the x-intercepts. You get -4, -1, and 1. So here it says, in which x-intercept does the graph cross the x-axis? Select the correct choice below, and if necessary, fill in the answer box to complete your choice. So here, in which x-intercept does the graph cross? Remember, we got two choices before. Either the graph crosses at the x-axis or it touches. So to determine whether or not it crosses or touches, we're talking about the multiplicity, right? The power of the exponent. If the power is odd, then it's not cross. So what do you say here? I have three x-intercepts, and their powers are what? X plus 4 to the first power is 1, that's odd. X plus 1 to the first power, that's odd. X minus 1 to the first power is odd. So they cross here. And all of them. And since there is no x-intercept with an even degree, then we say here for this last part that there are no x-intercepts that touches. All right, for that same problem, we just find the y-intercept. How do we find the y-intercept? What do we do there? Remember, to find the y-intercept, we do what to x? Set x equal to 0. And so for y. For y is the same thing as x, correct? So if I put 0, there's where I see x, I put a 0, and then it's a -4. So the y-intercept here is -4. Part D, there is no symmetry that I can tell there. So I think the next problem is very clear in terms of symmetry, but for this one, there is none. So this is that problem. So now here's what I did, and I was telling you about my method. Break up the number line based on the x-intercepts. So the first one I get from left to right is the -4, and then we come to -1, and then we get 1. So then I have 1, 2, 3, 4 sub-intervals. I want to just find a 5 here, test -2, test 0, so I test 2, looking for what sign do I get? So here, for f of -5, just plug that in. And so here I get the -5 plus 1 is -4. And then I get -5 minus 1 is -6. And then -5 plus 4 is -1. All I'm interested in is the sign. F of -2, plug that in. And you can look at it, that's typically what I do, is look at each one, plug in -2. So up here, that'll give me a negative for the first one. This should be negative. And then it should be positive. So I end up with positive. That's plus. Test 0 on this third interval, f of 0. We found that to be -4. That's negative. And then test f of 2 to be positive, positive, positive. So what does that mean? Well, let's look here. So I know that I have x-intercept at -4, -1, -1. I know the end behaviors. The end behaviors down here to the left is going to go down, right? And then over here on the right, it's going up. That's the end behavior. So check this out, and then look at those signs that I have there: negative, plus, negative, this is plus. So watch this. So negative is down, and when it gets from -4 to 1, -1 is positive, it's above. And it has to push down those x-intercepts, right? So then now from -1 to -1 is negative. It goes under the x-axis. It touches at the y-intercept, so it comes back up here. And then from 1 to positive infinity, it's positive. So it's good. That's how I used to do it.